Hi. So where we stopped last time was at the definition of the average current between in a certain time delta t. So remember the way it's defined. You take a cross section of a wire. You imagine cutting through the wire. You measure, if you want, the amount of charge going through the cross section in a time delta t, and the charge divided this amount of charge divided by the delta t gives you the current. So the current is in coulombs per second, which is the same as an ampere. Okay, it turns out that I'll have to modify slightly that equation. We have to be careful, and the problem has to do with signs. Delta Q, and I'll do an example in a minute, delta Q may be positive or negative. Now, in that equation, delta T is always a positive number, the time interval, that's always positive, but delta Q may be positive or negative. Now, we're going to take the direction of the current to be the direction of the flow of the positive charges, like I've mentioned in the previous video. I remember that really what's moving in the ordinary circuit are electrons, but for historical reasons, we pretend that they are positive charges instead moving in the wire, and the current gives the direction of the motion of those fictitious positive charges. And the reason we can do that is that if you look at the wire, and let's say you have electrons moving to the right, in terms of flow of charges, this is totally equivalent as having positive charges moving to the left. So if you don't care about looking at the atomic level, what is actually moving, you just look at the charge. If you have negative charges to the right, it's the same as positive charges moving to the left. So you can define the current to be the motion of positive charges, which are fictitious, but we're stuck with that convention. With that choice of the direction of the current, by the way, later this semester, at some point, we will have to consider cases where currents may be negative, positive, or negative. Okay, but for quite a while, we won't have to have negative currents, so we'll always have positive currents. So with that choice, the current is always a positive number. Now you see the problem. In this equation, if you look at this equation, we're facing a problem. Delta Q may be positive or negative. Delta T is always positive, so I average could come out to be negative, because if delta Q is negative, I average would be negative. So I have to modify that equation to ensure that the current is always positive. I'm going to actually use this equation. The average current is the absolute value of delta Q over delta T. So this is the symbol, those vertical bars are the symbol for the taking the absolute value. And remember what it does is simply that whenever this thing here is negative, taking the absolute value just means you drop the minus sign. So that way I average always comes out to be positive. Now, delta Q and I are actually always come actually with the choice of direction. Okay, so in that sense, you can think of them as a bit like being vectors. It's not always clear in books. They don't always emphasize that for the delta Q. That delta Q is always associated to a direction, so they're not always careful about that. You see what I mean in a minute. I'll do an example and it will become clear. So when we're given a delta Q, let's say in a question, we must also be given the direction that goes with delta Q. So when you're given a question and you're given the value of delta Q, you have to be told. You cannot figure out by yourself what's the direction of delta Q. You have to be told what it is. There's no formula or rule to figure out the direction of delta Q. Someone has to tell you. So it has to be stated in the question. Okay? So that's for the direction of the delta Q, that's to be given to you. For the current, like we just said, the direction of the current is taken to be the direction of the flow of positive charges. Okay, it will become clear right now. We'll do an example. For example, let's say you have a wire like this, and we're told the following information. In a certain time interval of 3 seconds, that's delta t, in those 3 seconds, there's a charge delta Q equal to minus 4 coulomb that goes to the right through the cross section. Okay, so during those 3 seconds, there's a total amount of charge of net charge of minus 4 coulomb that goes to the right. That means that so actually it's because there are electrons moving to the right and they carry a total charge of minus 4 coulomb. But in terms of those fictitious positive charges, having minus 4 Coulomb going to the right is totally equivalent to having plus 4 Coulomb going to the left. Okay, so we have to keep that in mind. Whenever you have negative charges moving in some direction, it's equivalent to having the positive charges moving in the opposite direction. So if you have minus 4 Coulomb going to the right, it's the same as having plus 4 Coulomb going to the left. Okay, that's just a statement of the problem. The question is, given this information, everything given here, we have to find the average current in that delta t in that wire. So when we ask the average current, we have to give two information because it's like a vector. We have to give the value of the current and the direction. Okay. How do you find the value? Well, you just apply the formula we saw before. The formula says take delta Q divided by delta T and take the actual value of the result. So delta Q over delta T gives minus 1, okay, minus 4 over 3. So that's if you keep 3 sig figs, because we're given everything with 3 sig figs, it gives minus 1.33 Coulomb per second, which is the same as an amp. So you get this ratio here is minus 1.33 amps. You take the actual value of this, you drop the minus sign, you get plus 1.33 amps. This is the average current. I forgot to write here that this is the average current here. So it should say I average. So that's the average current through this cross section here of the wire. That's just the value. Now we have to figure out the direction. So what's the direction of the current? Then we have to use this information here, that the delta Q was minus 4 Coulomb going to the right. So like we said, minus 4 Coulomb going to the right is equivalent to having plus 4 Coulomb going to the left. And because the current just follows the flow of those fictitious positive charges, the current has to go in the direction of the positive charges. So if you have 4 Coulomb plus 4 Coulomb going to the left, it means that the current, this average current, is actually to the left in this question here. So the final answer is that for this problem, the average current is 1.33 amps to the left. Okay? Now, sometimes instead of being given a delta t and a delta q, what we're given is the function q as a function of time. This gives the amount of charge going through a cross-section as a function of time. So in that case, how do you find the average current? You just apply the same equation. I average is delta q over delta t in actual value. But now because you have a function, how do you figure out delta q if you have a function? Well, it's simple. This, by the way, this is exactly the same as when you do mechanics and you have x of t, position of an object is a function of time. How do you find the average velocity? You do delta x over delta t. So how do you find delta x? You find the position at the final time minus the initial position. So if you want the average current between T1 and T2, you just take the charge at the final time minus the charge minus the charge at the initial time. So the charge at the final time minus the charge at the initial time. This gives you the delta Q, and you take the absolute value to get rid of a minus sign. Now, by the way, if you and then you divide by delta t. So this is the same as absolute value of delta Q over delta t. You might worry about the fact that when I wrote the equation for delta Q over delta t, I had absolute value over the whole thing like this here. But I don't need to take the absolute value all the way down because delta t is always positive. So I can actually just write it this way, and that's perfectly fine. So Q at the later time minus Q at the initial time divided by delta t, and you take the absolute value. Okay, that's if you're given a function of Q of t. What if, so this is like the equivalent of calculating an average velocity in mechanics. What if you're asked to find the instantaneous velocity of an object? If you have the function x of t and you want the instantaneous velocity at a given time, or do you find the velocity at a given time? You take the derivative of the position with respect to time. Same thing here. Let's say you ask what's the actual current at a specific time, the instantaneous current at a specific time. You take the derivative of the function q of t. So, and then you take the absolute value because again we want the current to be always a positive number. So you see you do dq dt the derivative of the function q of t, you take the absolute value, and that gives you the current at that time. Okay, this will be more clear with an example. So let's just do a quick example. We're told that you have a certain wire, the charge going through a cross section to the right, okay, so you're given this information here, is given by this function of time. This is a charge at any time going to the right in that section. Okay, now if you look at this equation, the units, there are no units shown anywhere. So actually, this is not strictly speaking correct, because you must be told what the units are. We could write the units in the equation, but the equation then looks really ugly. So another way of giving the information is to say this. The charge in this equation is in coulombs when the time is given in seconds. That means that to get a Q in coulomb here, you have to plug in the time in seconds. So if you're given a time in minutes, you have to convert it to seconds before you plug it in the equation. So whenever you plug a t in a time in seconds here, and you calculate Q of t, Q will come out to be in coulomb. Okay, 3 questions. How much charge goes through the surface to the right between 1 and 2 seconds? Question B, in that time interval between 1 and 2 seconds, what is the average current? And we have to give the direction and the value. And finally, what is the instantaneous current at t equal 2 seconds? Again, I didn't repeat that, but we have to give both the direction and the value. Okay, let's start with A. How much charge goes to the surface through the surface to the right between 1 and 2 seconds? This is just the net charge that goes to the surface, so this is just delta Q. Okay, so how do you do that? We calculate Q at the later time. So Q at 2 seconds, I just plug t equal 2 seconds in this equation here. So you have minus 3 multiplied by t cubed, so 2 cubed, plus 4 times t squared plus 8. And if you do this calculation just by pure luck here, there's no reason why it should be that value. It just happens to be by pure luck. When you do this calculation, minus 3 times 8, so minus 24 plus 16 plus 8, you get 0 coulomb. Okay, so that's the charge at 2 seconds. Now we calculate the charge at 1 second. You plug in again, now you plug t equal 1 here, you get 9 coulomb. So delta Q between 2 and 1 is Q at 2 seconds minus Q at 1 second. So it is 0 minus 9, you get minus 9 coulomb. And that's it. That's the charge that goes through that surface between 1 and 2 seconds. And it's the charge that goes to the right because we're given Q of t to the right. Now, in that time interval, what is the average current? Okay, and this is, so this is to the right because we're told that Q is to the right. Okay, now question B. What's the average current in that time? We just take the absolute value of delta Q, so absolute value of minus 9, divided by delta T. Delta T is T final minus T initial, so that just happens to be 2 minus 1, 1. Absolute value, we get 9 amps. This is the average current. Now, what's the direction of the average current? In that time interval, we just figure out that there's a negative charge to the right. That means that this is equivalent of having plus 9 coulomb to the left, which means that I average would be to the left because I average follows the direction of the motion of the positive charges. Okay. Now let's look at question C. What's the instantaneous current at t equal 2 seconds? So I of t is the absolute value of the derivative of Q of t. So just to, if you remember how to do a derivative, the derivative of minus 3t cubed, we differentiate with respect to time. So our variable is t here. We'll practice that in class. If it's not unclear, don't worry. We'll come back to that in the lecture. So you differentiate that with respect to time. Remember the derivative of t cubed is 3t squared. So minus 3t cubed, differentiate that, you get minus 3 times 3t squared, so you get minus 9t squared. Derivative of 4t squared, okay, derivative of t squared is 2t. So derivative of 4t squared is plus 8t. So we get that here. The derivative of 8, the derivative of a constant, there's no time there. This is a constant. Derivative of a constant is 0. So we get 0 for that. So derivative of this function here gives minus 9t squared plus 8t. Okay, this is the current at any time. Now, if we want the current at 2 seconds, we just plug t equal 2 seconds in the derivative. So you do that, you get minus 9 times 2 squared plus 8 times 2. So minus 18 plus, minus 36 plus 16. So we get minus 20. And we take the absolute value here, we get 20 amps. This is the instantaneous current at 2 seconds. Okay. Now, what's the direction? You see, our Q of t, when we took the derivative here, the derivative of Q of t was negative here. And remember that Q of t is defined with respect to the right. So if our Q of t, or the derivative of Q of t, was negative here, this is telling us that at that time, at 2 seconds, negative charges were moving to the right, because dq dt here is negative. So that means that at that instant, at 2 seconds, you have negative charges going to the section to the right, which means that the current has to be to the left, because you have negative charges moving to the right. The current is the motion, tracks down the motion of positive charges. So the current at that time is to the left. Okay, and that's it. Now, last comment, a special case. If a current is constant, so if a current doesn't change in time, it remains always the same value, then this is a special case. Then the flow of charges doesn't increase or decrease with time. You always have a constant flow of charges. In that case, first of all, the average current, if you do the average current between, let's say, 1 and 2 seconds, or between 2 and 4 seconds, or between 5 and 6 seconds, usually when you do the average current, you get different values for all the different delta t. But in the case of a current that is constant, obviously the average value always gives the same value, because the current stays the same. So no matter what you use for T1 and T2, you always get the same value. Another way of saying that is that if the current is constant, the average current gives the same value as the instantaneous current, because the current doesn't change anyway. So doing the average or the instantaneous value always gives you the same value. So the two equations, the two formula for average or instantaneous always gives you the same value for a current constant. This is the same as in mechanics. If you have an object moving at constant velocity, then average velocity and instantaneous velocity are the same. And finally, of course, if the current is constant, then the function I of t is a constant in time. It does not depend on time. What I mean by that is, for example, I of t could be 4 amps. The key point here is that if the current is a constant in time, you see there's no time there. It's not 4 times t or 4t squared or 4 log of t or sine of t. There's no time dependence here. That means that the current here stays equal to 4 at any time. So this is a special case of constant current, and that would be a very important special case that we'll be working with often. Okay, so I'll stop here. Thank you.